welcome everyone to my presentation about my intern project in Microsoft, which the topic is the .NET malware dynamic instrumentation. And my name is Hexiang Hu, and I'm an intern at Microsoft. And Steven and Jeff is my mentor for this project, and they helped me a lot about the project. Okay, so first, let me give you guys a brief introduction to the background of my project. Since it's a .NET project, so it should be related with MSIL, the Common Intermediate Language. Some of you may know that very like Java bytecode, Common Intermediate Language is an intermediate language defined by Common Language Infrastructure Specification, which is used for .NET framework. It enables programmers to develop cross-platform and language-independent application for Windows. And as it is a really convenient framework to develop, it also comes with some run size for the virus writers, so that it also provides the virus writer a really convenient environment to produce their cross-platform malwares. So then I would like to introduce you with about .NET malwares. And first, let's take a look at this graph. This is actually, as you can see here, it's actually the monthly unique MSIL malware machine count from January 2013 to this August. And as you can see that we could find the general trends of this graph indicates that MSIL malware is actually a growing problem. So that we may indicate that there should be more attention to be paid to this category of malware. And for the study of MSIL malware, the biggest problem is, as you may know, that it's the .NET Packer. So next, I would like to show some knowledge about the .NET Packer. And actually, a large number of .NET malware families are using various custom or commercial .NET Packer to obfuscate and pack their code. The packers may serve the functionality as destroy the original data structure of the malware and hide or encrypt the important string and function name of the metadata, and also change the original control flow of the program, which makes analyzing really suffer. And here comes the purpose of my project. My dynamic instrumentation framework is actually designed to get rid of the bad effect brought from these packers and to retrieve .NET internal function information during its runtime. And for this purpose, actually, I did two different attempts of implementations towards it, and then I would like to share them with you guys. And the first attempt is about a jet compile hooking method with some reverse engineering into the .NET platform. The infrastructure goes like this. As you can see here, just-in-time hooking logger is what I developed, and it will first query the interface from corgit.dll to get the function getJIT function. And with calling this function, it will return me the address. It will return me the address of the interface of icorgit compiler. And inside this icorgit compiler, I will do the hooking to its compile method, so that every time a malware process is trying to call the compile method during its running time, it will first go into my log function, which will access some internal data structure and then output the internal functions. And after the log process, it will call back to the original compile function and do the usual things as .NET. And the advantage of this implementation is that it's almost invisible for the .NET packers, so they might not be able to notify that what I did about the parameter or about the information of the compiling code. However, With these simple and straightforward implementations, actually there comes with some problems, so I did my second attempt. And the problem with this one actually goes with 3 categories. And the first, that because I'm doing like blind hooking, which I do some reverse engineering into the .NET platform, so it's really time consuming and it's really hard to support all versions. Since that when I was going to do a really simple modification, to do a really simple improvement of the hooking method, it will cost me a lot of time to do the reverse engineering, to find those corresponding internal functions which will lead me to get the information about the internal structure. And the second problem is that with this compile method hooking, it will only enable me to log the information at its compilation time, as opposite to the every time it is called, which means that I may be not able to access the function stack during its runtime, so that I cannot get any information about the argument value, which might be really valuable for the virus research. And the third is about some malware which are obfuscated with some pre-jitted functions. So they might pre-jit and compile their methods into the binary, into the assembly code, which my tool will definitely not be able to record any information. And that's obviously a really big problem. So after some consideration about this implementation and after some studies, I find it's really hard to implement all the purposes. So I eventually abandoned these methods and unfortunately I find another, which is a .NET instrumentation based on a Microsoft released profiling framework. And the core technology here is, as I have mentioned, that is the profiling API, which I would, based on this API, and develop a COM DLL object that inherent these two interfaces, which is ICOR profiler callback and ICOR profiler info. And with the info interface, it enables me to retrieve the information of the .NET internal structure. And with the callback interface, I am enabled to get the control when there is some .NET CLR internal event appears. And the general infrastructure goes like here. First, we have a malware process which is running CLR runtime. And when it launches itself, the CLR will first check if there is 3 environment variables, as it shows here, are correctly set it up. And after they check it, if it's correctly set up, it will load my customized profiler DLL into the process, which will make the profiler unable to terminate it, since it will terminate the process. And this DLL will interact with the interface I mentioned before to get some information. And it initialized with a set event leave function hook, which will enable my function get the control when there is when the CLR is going to enter a function, leave a function, tell core function, and when its compilation is finished, or when its compilation search is finished. And then I will get the access to the internal data and output it into 3 different data files. However, even with these implementations, actually it comes with a lot of challenges, since I group them into 2 categories. And the first is to parsing the argument parameter value. And the second is problem with the generic information representation. And it comes with these 5 events, which is actually, which I have a really hard time, which is the hard time I have with the undocumented .NET internal variable type parsing, and the program runtime parameter value retrieval, and the anti-profiling techniques, and the representation of function and the arguments regarding to a function. I will talk with these topics in detail in the following slides. And first, let's start with undocumented internal type parsing. Fortunately, actually, there is an open source version of CLR Profiler, and it's a Microsoft release source code, so we can refer to that one and get a lot of .NET internal types being correctly parsed. However, with my project, I find that there is some types that are not fully supported, which is a generic type. So here I would like to talk more detail about the generic type. And if you look all those source code, you will find that there is a phase that gets a signature blob from the .NET internal data. So and then parse the functions types through this signature blob. And I find that with this signal blob for the generic type, it first comes with a value of enumeration type, which is element type generic inst. And then the second of this signature blob comes with a number n, which stands for the number, which indicates the dimension, the number of dimensions that this generic type have. And then it follows with n signature blob, which everyone will indicate a token that the token of the corresponding dimension, and it will indicate which type of this dimension is. And after that, I will talk about the runtime parameter value retrieval. And here I would introduce a new technique, which is also from the profiling API, and it's called the shadow stack. And the official definition is here, but it seems like not really makes sense. And I would like to talk my understanding. I think it's actually give you the access to the function stack during its enter and leave time, so that every time a function instance is called, it will first go into the enter step and then access the argument info value, which contains the argument type, argument's address and its value. And then it will go into its, and then it will go into the function IL body to execute the function IL code. And after that, it will go out first to my leave stump, which I can access its return value. And after I finish my access, then it will return the function result. And this actually means a lot to the profiling. And I will talk some advantage of that one slide after, which is in the anti-profiling. As you may know that with the current commercial obfuscator, it is really popular for them to avoid the profiling with checking environment variable. But is it a really definite solution for avoiding the anti-profiling? I think it may be not, because I have just solved it with the shadow stack method. I identify the function that is used for checking the environment variable and hook it, modify its return value in the shadow stack, so it may no longer detect correctly about my profiling. And you may argue that there might be some more advanced anti-profiling technique. However, I think if these anti-profiling techniques are implemented with managed code, and if you can find them out, you can also do what I did here to modify its detection result so that it might no longer work. And after I have finished the stuff about the internal value parsing, I would like to show you the idea of information presentation, which here I use a method called generic hash. And with this generic hash value, actually, what I did is to exclude all these immediate value and the function tokens, and only take the opcode and hash the opcode and get a hash value to identify the function. And for some really simple IR obfuscations, they may doing things like add a lot of nonsense nope into the IR code. So here I would do a simple anti-IR obfuscation with exclude all this nope, so that it might have a better result. And for the representation of the argument value regarding to a function, here I use a generic argument value hash, which actually takes the IR opcode and the argument value in its string format and hash it to represent the argument value. And here is the data output of my method. And as we can see here, we get the function signature, the function generic checksum, and full checksum and IR assembly, as well as its argument information and its return value information. And that's all about my implementations of the .NET malware. So next, let's evaluate how my dynamic instrumentation tool performs by looking into a specific case of .NET malware, which is Bladabindi. And first, let me introduce what is Bladabindi. And I would like to show first the impact of Bladabindi. As you can see here, it's a backdoor function. And if you remember that we have a graph here, which indicates the general trends of the .NET malware. And you will find that at the bottom, there is a large blue area, which actually fits quite well with the shape of the general trends, which means that it provides a lot of samples. This category provides a lot of samples of .NET malware, and it's a backdoor, and it's actually the backdoor category. And Bladabindi is a backdoor malware which actually have over 90% of the general backdoor category. So I might think that Bladabindi is a particular problem. It's a really typical .NET malware problem, and it will be worthwhile for us to analyze this one to represent the case of all .NET malware. And next, I will do what is Bladabindi. In general, it's a backdoor, and it can serve as keylogger and provide remote access to the to the bad guys. And also it will do like USB spread and something else I didn't write here. And it also uses various of commercial obfuscators such as a really popular one, .NET Reactor and Smart Assembly and Deep C and a Crypto Obfuscator and a Confuser. And to evaluate my project's impact over the detection, I did actually two different steps. With the first one is to validate the profiled log with regards to the actual malware behavior. And with the second one is to evaluate the generic detection impact my methods bring about. So first, let's do the behavior validation. As you can see here, with the left column, there is some malware behavior regarding to this specific Bladabindi sample, and in the right we can find that there is a we can find that in my profile logs there is actually every corresponding function level information about this behavior, which you can see like if they are dropping a virus file in a temporary directory, we will find that they are doing some file writing. And if they are modified the system firewall setting, we will find that there is a VB function shell that net shell to enable the firewall access to this program. And also, when they are going to like build up a backdoor connection, there will be a correspondence TCP client constructed. So you can see that it might be a really good candidate for the virus researcher to look through this profile log and to analyze the behavior of the virus. But however, I should say that this is not even the most exciting part of my project. The most exciting part of my project is actually the generic detection impact it brings about. And here you can see there are two different Bladabindi samples which are obfuscated with different obfuscators. One is YAML and one is customized obfuscator. And with my dynamic instrumentation tool, after I filter the massive data, I find that there is two lists of Bladabindi internal functions. And we will see that there is a really strong correspondency into their generic checksum. So we can see that it might be really good for some, probably not human analysis, but the machine learning-based analysis to categorize and clustering the .NET malware. And the statistics goes like this. And for the Bladabindi case, I did an experiment with 585 random samples out of around 4,500 samples. And with all these 585 samples, I find that all of them are successfully profiled, but only 369 of them are successfully behaved inside the virtual machine. Since that I didn't do stuff like to do the avoidance of anti-VM and some other stuff, so I will talk later. So here's the successful behavior. I mean that they are doing the right job as they are expected to. And we can find that in the following list, there is actually a really good detection ratio of these Bladabindi internal functions. Actually, the function, you can ignore the function signature since they might have the different name, but they might have the same generic checksum. And here the lower bound is the detected SHA-1 divided by the total SHA-1. I include all those not successfully run SHA-1 also. And the upper bound here is the detected SHA-1 versus the good SHA-1. And we can see that the detection ratio might be over 0.5 to 0.9. And I can definitely say that it might be much higher than the lower bound, but would be lower than the upper bound, or maybe around the upper bound, since I don't know the other samples, how they are performing. So the analysis for this dynamic instrumentation tools first came with obfuscator cases. With all these 500 and almost 600 samples, I have these falling obfuscator detected, and they are what in the successfully profiled logs, and they are actually being well profiled. And I can say that my methods works well with them. And however, since it's not a one-shot solution to the .NET malware detection, so there also comes with some problems. And I categorize them into two. And the first is the problem with samples that are not running correctly. And I divide the reason into three parts, since I have did research into those samples and find that some of them are doing stuff like anti-VM techniques. And of course, some of them are doing anti-profiling. Since I didn't handle every anti-profiling cases, I just handle the most popular one, which is checking environment variable. And also, because I was doing the batch processing with user privilege restriction, so that when some malware is going to ask me to elevate their privilege, I just ignore them, so it might not generate good result. And also, there may be a problem with the generic IL checksum. Seems that they might do more advanced IL obfuscation, like insert garbage IL code, which make no sense, like push, pop, and search and some other patterns of IL garbage code. So, but we can probably figure it out by maybe set up a database that stores all those garbage patterns and make our generic checksum more generic. And after we have already studied about the result of the Bladabindi case, I would then talk a little bit about the future machine learning application to this to the data provided by my dynamic instrumentation tool. And first, let's recap with the argument hash. You might remember that I didn't make use of this argument hash, but actually for every argument in a function instance, the argument hash will take the hash value of the generic IL opcode and plus the argument value, which might bind the argument value with the function IL opcode, and so that we can use it to identify the specific behavior regarding to the argument in a function instance, such as for this one, which is a VB function that's going to set up the firewall, and we might calculate its checksum and add it to the argument hash list, so that we can let the machine to learn about the program's behavior, specific behavior. So that we might, so that I propose that there might be a potential application for, with these two categories, which is auto-classification and auto-clustering, with the usage of the generic representation of function information and argument information. And I believe that this dynamic instrumentation tool will help future machine learning-based detection through these two categories. And yeah, and that's all about my presentation. And thank you for your patience. And if there is any questions, now is the time to ask. And if I can answer you, I may.